So enough for the limit. This time you have to take a more desperate look into the applications of limits, right? Now, limit theorem was the foundation for differentiation, right? So the whole point of differentiation is we were trying to find a difference the so small so that the limits of the difference approaches zero, and would understand that statement very simple. Let's take a look at these few lines of reading. So, if a function be defined in a delta dilated neighborhood of a point, if the function can be made very close to L by choosing a x sufficiently close to x, right? So, what we are saying is the limit of a function, right? As the function approaches some x naught is L, right? Very simple. Now, there are scenarios where you try to take left-handed limits and right-handed limits. Now, most of the time, this is the same, but we'll realize a special type of function. They are called discontinuous, right? They have a bit of peculiar scenario, so don't worry much. So, for example, we have these few examples, and we would like to show that the limits are the same. So, usually, what you do is this. It says you have to find the limit as x approaches 0 of now 2x plus 1, right? Now you realize that we are approaching 0. You realize that previous limit we are approaching infinity, right? But this limit you are trying to approach 0. And what you do is that you actually watch the sign on the limit. So this is a left-handed limit, right? So what you're actually doing is that we are choosing a very small, very, very small negative number, right? We are trying to see that almost the smallest negative number of this function, what will it be, right? Yes, so that's what we are trying to see. And it might not sound as much, but that's how what limit is trying to do, right? Finding the smallest negative number. And that was the whole point of learning the whole delta neighborhood, related neighborhood, was just trying to see that if a function approaches a particular value, right, how would it affect it? And so that's what it is. So, but you see, you have to substitute 0 into this function, right? But now, specifically, I substitute negative 0, but negative 0 is still 0, right? So that's what it is. So when you substitute 0 into this function, you get 1. Um, Now, there's the right-handed limit. When you do same, you also get positive 1, right? So it's a bit of a misnomer, but just know that the right-handed limit, right, is usually given as x approaches x minus, and the left-handed limit is x approaches what x plus, right? And that's it. So this one, we're asked to approach this one. Now, when you see this, right, don't be confused. 1 over 0 is undefined, right? There is no mathematician who knows what 1 over 0 is. However, here, look at, we are trying to approach what a value so small, right? For what the function 1 over x. The value is very close to 0, but it's from the negative direction, and it's for the function 1 over x, right? Now, some people can assume that, oh, because here we substituted 0, then why don't you substitute 0 for here? Now, the truth is here, we didn't actually substitute 0. We substituted a number so close and so small that the number can be assumed to be 0. It's actually the same concept to use here, right? So if the number is exactly 0, we don't have an answer, right? But we just want a number which is so close and so approaching to 0, right? And how do we do this? Well, it's usually from observation, right? So you can try, let's take numbers very close to 0. So from the negative direction, so we can try negative 0.1, negative 0.01, then negative 0.001. Realize that this is greater than this, and this one is also greater than this, right? Now, when you try to find 1 over x using this as your x's, you realize that this one will give you 10, this one will give you 100. So 1 over negative 10, negative 100. And this one will give you a minus 1000, right? Now, what do you observe? You observe that as the value gets very closer to 0, right? As the number of zeros in front of the number before the original number increases, right? You realize that you start getting very big numbers or very large negative numbers. So, if I have to put it that way. Now, the concept then evolves that fine. Since we realize that we are approaching very large numbers, then we are approaching infinity. However, 1 over 0 is undefined in maths, right? But we only see that the limit as x approaches this is infinity because it's an observation that you realize that as x approaches very, very small values, you approach infinity. And now that's the same thing you can do for this one. But this one just use very small positive numbers, right? And it will still work, right? So those are the two things I would like you to note here. We are not substituting 0, we are substituting a value which is so small and so close to 0, right? And that's it. So you realize that our observation would be more realistic the more the very closer the number is to 0. Okay. So there are other ones, right? For example, there is limit as tan inverse of what? 1 over x, right? As x approaches 0. Now, usually, if you have questions like this, right? Usually, these are transcendental functions, right? And you should probably know how their graph looks like, right? So, I think I'll show you some of the graphs. So, this is our inverse tan function, right? Um, Probably you've not seen it in your course study outline, right? But it's nothing much. So this is the inverse tangent function. Now you realize that this line here, right? It will never touch this curve, neither will this line, right? We call it an asymptote, right? So when you are asked to evaluate the tangent of these functions, right? It is usually coming from memory, like you already know how the graph looks like. So first, let's forget about the tan inverse outside. Let's consider what is inside. Now, when you find the left-handed limit as x approaches 0 for this one, you get infinity, right? So it means that in essence, this question can be said to be you doing what? Tan inverse of what? Um, yes, tan inverse of infinity, right? Now, tan inverse of infinity means that you have infinity on the y-axis and the angle on the what? X-axis, right? Now, when you look at this graph, right, you realize that as you go up, you are going in increasing value of what? Y, right? So infinity will appear at a very, very far value. And remember, this line here, it will continue try to approach and touch this line, right? Yes, it will try to be touching this line, right? But it will touch it at a very far point. So we see that far point is infinity, right? Now, since we are finding tan inverse, it means that when we trace on the x, we'll get what? Pi over 2, right? So that's why the answer here is minus pi over 2 because we are doing the left-handed limit. So we'll get negative infinity, right? If we are using tan inverse of, we are doing the left-handed limit, then we'll be tracing from this direction, right? This lower direction. But since we are, yes, so since that was that. Now, when we are doing the right-handed limit, we'll be tracing from the positive direction, so this direction. And yeah, the definition doesn't change. So that's for the tangent function, right? Now, I would just like you to just appreciate the curves and why they have those limits. We will go into the proper integrals of them later, right? Now, there are times when you can have functions defined in weird way, right? You remember all your previous studies, you just had either polynomial or algebraic functions, right? Very simple functions which are continuous in x, right? But at the advanced level, this changes a bit. At the advanced level, we try to conceptualize more of a digital domain, that there is a cutoff, right? And those functions are usually defined in a piecewise version, like there is a value for only few sections of it, right? So for example, this function is defined as the function is 1 whenever x is greater than 0, right? And the function is what? -1 whenever x is less than 0. So let's take a look at it. So the function is 1 whenever x is what? Greater than 0, and -1 when x is what? Less than 0. Now, you are asked to find the left-handed limit, right? That is, you are approaching it from the negative direction, right? Now, when you're approaching it from the negative direction, right, it means that you never touch this line, but you've come so close to this line. In essence, your value will be still what? -1, right? So you see, there are times where the left-handed limit will not be equal to the right-handed limit. Unlike the previous ones where you had the continuous case, the left-handed limit and the right-handed limit matched, right? So these ones, the left-handed and the right-handed limit match. Some, the left-handed and the right-handed limits don't match, right? And those are usually discontinuous cases. So you should watch out for them, right? And what they are trying to let you appreciate is that not all functions are continuous. Some are actually discontinuous, right? So the above, yes, I think this one pretty much explains what we just read above. And we are asked to prove, this is a work example, and I'm sure you can be able to prove that, especially given that you already have knowledge on the Bose-Einstein theorem, right? So we'll go ahead. Let's now review some special theorems. Now, there are some limits which you should know, right? These are special limits, and the proof is quite complicated, a lot of geometry, but you should know them. I mean, you should keep it ahead. So when you have sine x over x, right, the limit as x approaches 0 of this function is 1, right? And it's common, probably you even did it in SHS. It's actually very profound, and we'll have examples on that. The second special limit I would like us to see is the e function, right? Now, when you have limit of 1 plus 1 over x raised to the power x, and this limit tries to approach infinity, you will get e, right? And that's actually the definition for the Euler's constant. Now, the reverse for the x's are true. When the x inside becomes just x and the x outside becomes 1 over x. As this time you approach 0, right, you also get e. And these are just special limits, right? You usually use them in proofs or just conclusions, right? They wouldn't really require you to prove why they are that, right? Unless you get to a topic called a series, called Maclaurin series and Taylor series. That's where you usually prove these things. But for now, for the basic level, let's just keep this one ahead because questions might appear on them and we may use them. Yes, so that brings us to the end of this session. Continue to ask questions on the platform and give your contributions, as well as continue to like, share, and subscribe this video. Thank you very much.